Hmm. All right. So we talked about ISAs. We talked about how they get, well, we've talked about how ISAs are implemented, right? Like physically implemented with microarchitectures and how your CPU needs to implement some form of microarchitecture and build on top of it in order to do stuff, right? Then uh, we've talked about some of the difference between the few. For example, ARM making you build your own physical or virtual addresses so that you can actually do stuff with that. RISC being generally more simple, or yeah, generally more simple in what you can do, meaning that you would have to take more instructions, or you generally require more instructions in order to do the same thing as x86, and then obviously ARM took more because we had to build our own virtual address, right? So let's talk about the CPU that's gonna actually doing that stuff, right? All right. So here's the thing with the CPU. The CPU does like 5 things over and over and over and over until it gets shut off, right? That's all a CPU really does. And that instructions or the things that it does is called an instruction cycle, right? An instruction cycle, the most basic one is called a fetch decode execute cycle, right? It fetches what it needs to get, it decodes it, or it decodes it, it gets all the necessary elements that need to be there so it can execute whatever it needs to execute, and then it executes it, right? And we'll be talking about a 5-stage, right? Which is a little bit more in detail. Okay, 5-stage, and then it is instructioned, or sorry, it is pipelined, which we will talk about later. hmm Okay, first thing, instruction fetch, right? You fetch an instruction. What does that mean? Well, in your code, right? In your code, you have your code section, and your code section is numbered, right? Code section is numbered with memory addresses, right? You have to go to a certain memory address in RAM to access the current code instruction, right? hmm Okay, that's a little bit of oversimplification, or that's a little bit of a lie, but we'll handle that for now. Okay, so we have code like 1, 2, 3, 4. Okay, okay. So whenever we start, we'll start with a 1, then we go 2, 3, 4, 5, and these are all instructions. So our program counter, which is the register, we talked about registers before. They're the most used memory element, and they're very quick in the CPU. They're stored in the CPU, and they're very quick, right? What a program counter does is it stores the current instruction, that is the memory address of the current instruction that we're going to be executing on, and it says, okay, what is the instruction, right? Okay. So it fetches that. It gets the instruction. Then it does the same decode, remember? And it's slash register fetch, right? So in order to understand that register fetch part, let's look at an example of like an add, for example. Okay, we have an add RAX3. In order for us to actually go about executing this add instruction, and it will be executed in the execute step, but in order for us to do that, we first need to know what the value of RX is, right? RX is once again a register, but we need to know the value of RX. And during the decode stage, we would go to the places where register is stored. We'd get the value. We'd add 3, or we wouldn't add 3, or we'd give the execute step the value of RAX and 3, and we'd let execute just add the two together, all right? Okay. Mem access. Mem access works for load and store, right? Whenever we're loading, whenever we're storing, it'll happen here. Mm. Okay. Then write back. Write back. Okay. Let's say RAX was 4. So 4 plus 3 is 7, right? 7. Okay. 4 plus 3 is 7. We need to send that back to RAX, right? We need to send that value right back to RAX so that it can actually be done with it, right? That happens in the write back stage, right? The value is updated and written back to. All right. Pipelining. So you kind of noticed how once instruction fetch happens, right? Instruction fetch happens and then well, you've done the first instruction fetch. That does like all of a sudden you're doing nothing, right? But you can fetch the next instruction and just have it run while your previous instruction is running, right? Sort of in the cascade that is shown above, right? You can do that, and that's what most computers do, right? They have a thing called a pipeline where they follow this structure where the first cycle instruction fetch, right? Second second cycle this instruction fetches, then this instruction fetches, then this instruction fetches. So every single cycle instruction fetch is running. In fact, all the stages are running. So they can have theoretically 5 times the amount of instructions running, right? Instead of having 5 times as fast, which you could have done, you do 5 times as many instructions, right? Yeah. And then this is a thing called parallelism. Parallelism is you'll see it. I hope to sort of get it in your mind right now because you'll see it a lot. Parallelism specifically, you'll see it a lot, and you need to know it. So yeah. And then specifically, this is called instruction level parallelism, which means that you're doing instructions in parallel, which is you'll see this like ILP or instruction level parallelism, and then you'll also see something like data level or maybe like a register level or just like whatever you're applying any amount of parallelism to, you'll always see blank level parallelism, right? You'll see that a lot. hmm And then once we're doing this, we get to things called hazards. Like once we're doing ILP here, we get to things called hazards, and then things get messed up, right? First hazard we'll talk about is called a control hazard, right? Just hear me out. Imagine, I don't know if this is fully true, but imagine that we do a compare and it's in the ALU and we compare on line 4 and it says to jump to address 8, right? Go to 8. Now, if the pipeline has 5, 6, and 7 in there, then 5, 6, and 7 are completely meaningless now. Like we don't want them to run. We want 8, 9, and 10 to run, right? So we have to completely erase them from the pipeline and reset. Okay? Mm. That's called a control hazard. And whenever we do that, we have to flush the rest of the existing pipeline, right? Okay. Then we have what's called a structural hazard, right? Let's assume for a second that I have the load on this instruction, right? So it would load here. Let's say it loads RBX. Let's say this next instruction is an add, right? So we're adding RAX or RBX as well. These two are both on this instruction cycle. Both of these are using RBX on the same instruction cycle. So it's possible that we could have a problem where this instruct this instruction loads RBX after this one writes to RBX, right? So this RBX gets updated, then this reads or this loads RBX, and then this one has the wrong version of RBX, right? So this one, the value it's getting is just wrong. Mhm. That's called a structural hazard. And you can solve that by doing something called data forwarding, right? Data forwarding is like, okay, this is my add. I have added here, and then then I won't wait for the write back. I will quickly go to, I will broadcast to anything that's already live saying, hey, this has been updated, right? hmm All right, last one's a data hazard. Add RX4, add, okay, RAX for RBX, and then this one also requires RBX, right? So this one can go on its own completely fine, right? So if this one is the first instruction, the second instruction, or the third instruction, it does not matter, right? This one can be in any order this one can be done. This one has to happen after this one, right? So this one has to happen first, then this one has to go second. So this one can either go first, second, third, or first, second, third, right? That's how it has to work, right? That's called a dependency or a data hazard, right? Where one thing relies on the other in order to get proper information, right? And yeah, those are just some of the basics of pipelining, right? And we'll look into it in the future, but right now, let's talk about threading. What is a thread, right? A thread is, you can imagine a thread as a instance of a process in the same memory as your other process, or as a couple of other processes, right? So they share an address space, right? They share an address space. And why would you use this? Well, you use this to cover up whenever something is going for I/O, right? So have you have like four threads open. One thing goes for I/O, the thread takes over, right? hmm And yeah, so threads share memory. One thing they don't share is stack, right? They don't share stack. That's very, very important to know. You can see it here. And then also threading is you'll hear threading as concurrency. Concurrency is whenever you're doing something in this or this format, wherever. Yeah. Okay. Let's talk about types of memory now. Let's go back to this SIMD vector. Okay. Well, we talked about ILP, right? And we talked about covering the fact that you have to go in and get information with concurrency, right? Well, now we're going to be talking about data level parallelism. All right, which is, okay. In order to do data level parallelism, you use what's called a vector register, right? Which basically means that it, and okay, so you'd perform an operation on data at the same time, right? So you'd have multiple pieces of data and you'd perform the same operation on them at the same time, right? So you'd have this. This is one reg. This is another reg, right? And you perform an operation on them, right? Operation, operation on them simultaneously, right? So let's say I do an add where, actually, let's just add as many regs as I want. Okay, I'll do another one reg here. We'll do one reg here. Alright. Okay, these are 4 registers, right? 4 registers. What we do with this is we perform the same operation on all of these. So let's say we perform an add on all of this where we add 3 to every single one of these. And we do that in all of that in one instruction cycle, right? So we'd say we give a specialized opcode, right? Our specialized opcode that says do a, I don't know, vector add, right? On a special register that would combine the value of these 4. They would combine into a single register, a truly single register, right? And that's called a vector register. So one vector register. So we do like an opcode vad, and then we do vector add, and we would say like 3 or something, right? Vector add, I don't know. Let's say v1 or vector 1, 3, and we do this, and in doing that, we'd be able to add 3 to every single one of these at the same time, right? hmm Okay, let's say something real quick. I've talked to you about like CPU, right? And we said RAM is here, and then we have disk at SSD, right? And we've talked about, having NVMe to access this, and we've talked about address spaces being stored in RAM, and we haven't really talked about the fact that accessing from RAM is slow. It's far too slow, right? We cannot access from RAM because of how slow it is, right? Or like it would not be feasible to access from RAM. So what do we do? What we do is we have a little smaller piece of memory, right? We have a smaller piece of memory that's faster to access than RAM that can just store what we need to, like what we need to have on hand, right? So that's called a cache. And in fact, there's not just one cache. There's usually 3, right? There's usually a small cache, a slightly bigger cache, which is called L2, L1, and then L3 cache, which L3 cache is usually very big like this, right? And actually, this is usually inside of the CPU a little bit. Shoom. And then this is inside the CPU almost, right? hmm Okay, talked about this, and we talked about how transistors make up the CPU. Transistors make up logic gates by having that and or pattern we talked about. We talked about how that and or pattern makes up logic, or yeah, we already talked about logic gates. We talked about how you can use logic gates in either a combinational or a sequential way. Sequential way being you care about your inputs or eh, your outputs map to your inputs so you can continuously repeat giving yourself the same information over and over and remember stuff, right? And we talked about how sequential and combinational memory could be combined together to make a flip-flop, and then a flip-flop is an edge trigger thing where you could combine flip-flops together to make a register. That's right. Talked about all of this. Registers is the most used memory element in your computer. It's inside of your CPU, right? A reg. Okay, we have registers here, and we also talked about register files, which is, collection, like a 2D collection of registers, right? And you're more than likely going to access register files a lot, right? What L1 cache is a well, it's another form of memory, right? Usually, this form of memory is shown in a pyramid where reg is like the top of the pyramid, where it's fastest. Then L1, L2, L3 cache are in the pyramid. RAM is sort of at the base or near the base, and then SSD is the base, and it shows access speeds being really, really slow for SSD because it is. SSD takes a long time to access. Even RAM takes an unacceptable amount of time to access, right? But caches don't take as much time to access, right? Mhm. Okay. Let's look at policies, right? Cache policies. Okay. What is cache policies? Okay. Uh, wait, which policy am I talking about? Policy placement right back. Oh, policies over here. Okay. So there's a couple. Well, actually, you can design a cache in so many different ways, and I mean so many different ways, right? Mm. So you can design a cache in a lot of different ways, and we'll sort of go into the three main ways that you can actually go about doing that. But the first way is with placement, right? Do you either want with placement, do you want your cache to be a bunch uh I forgot. Okay. Cache is a collection of what's called word lines. Collection of word lines, right? So let's say we have, I don't know, let's do 8. 1, 2, 3, 8, right? So these are all 8 word lines, right? Right? So how do we split these up, right? Because, mm, okay, actually, no, let's talk about reading from a cache, right? When you read from a cache, right? When you read from a cache, you access a thing called a tag, right? This tag, what this tag does is it's the thing that you use to identify which word line that you want, or cache line, sorry, which cache line you want to access, right? Do you, okay. So if your tags match up, right? Because you will check every single tag at the same time. There is hardware to do that, right? You check every single tag at the same time, and if you get a hit, then it's called a cache hit, and the contents of your thing, of your tag, the contents of the cache with the contents of your cache are output, right? And you can use them. Otherwise, the stuff you want is not in the cache, and you need to look elsewhere. Or you need to go to either L2 and L3 cache, or you need to go to RAM, right? Mhm. Okay. So there's a couple ways you can sort of have this organization structure, right? First thing, how do we well, checking every single tag at the same time is expensive. So if you want to make it cheaper, right, you can have what is called a set, right? And let's say 1, 2, 3, 4. You can have this be set 1 and this be set 2, right? Set 1, set 2. Okay. And then you would you would first check which set am I in, right? Which set do I need to go to? And then you check every single tag in those sets, right? So that like in this case it would have the amount of tags you need to check, right? And when you have it something like this, it's called a set associative array or cache, right? Set associative cache, which has two caches or two sets. I'm sorry. Mhm. Okay. Here you are chilling. Mhm. Okay. Here's the thing. What the word or the name for having everything be a set is called full associative, right? We have a full associative thing when every cache line is just in one set, right? Then on the other extreme, when we have every cache line has its own set, right? That's called a direct mapped cache, right? These these two extremes are used in specific cases, which we won't talk about, right? But yeah, they're used in specific cases, but set associative is used most often. Okay, so you go to your set and you get your content to your cache, and then what do you do? Mm. Oh, well, you use it obviously. So you'll cycle, and stuff will get added to your cache. And if we assume this is a set, this is also a set, right? So okay, let's say uh, filled, 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 and I want to add something into this set, right? How do we do that? Well, we do that by kicking something out, right? Which one do we want to kick out? Well, you kick it out based on the replacement policy. So you can, or one replacement policy is literally just randomly hit, right? Another replacement policy is to say which one is not being used, like which is the least recently used, and then we would kick that one. All right, right. That is one policy, right? Okay, that's that's it for eviction policies, right? Whenever we're too full on cache stuff, we can throw away our stuff and be fine. Mm? All right. Okay. hmm And then a write back policy. Okay, write back policy. Okay, write back. What is write back? Write back is basically you have you have a value in your cache, right? And let's say the CPU is over here. The CPU takes your value from your cache. It's now in the CPU. Let's say you add this value, right? You add to this value. Well, obviously, we know the instruction cycle: fetch, decode, execute, memory, uh, memory, and a write back. We need this write back is important because now the value in your cache and the value in your CPU are completely different. So in order to, there are three real ways to handle writing, okay? And they involve RAM, cache, and CPU. Okay. First thing that can happen is you can write to cache and you can write to RAM, right? So now both are updated. Another thing you can do, don't write to RAM, write to cache. And the final thing you can do is just write to RAM, don't write to cache, right? Those are your write back policies. And that is pretty much it for caches. hmm Yeah.